Okay, good day class. So we are now on the last part of mass transfer in various geometries. So the first part that we discussed in here was the dimensionless numbers that were used to correlate data. And the second part was mass transfer for flow inside pipes. And this is the last, and this is the third and the last. So mass transfer for flow outside solid surfaces. Now, under this particular part, we're going to have a mass transfer in flow parallel to flat plates, the first part. The second part would be mass transfer in flow outside a sphere or using a geometry that of the sphere. And the third one is mass transfer through packed beds. So let's go into first the flow parallel to flat plates. Now, the mass transfer and vaporization of liquids from a plate or flat surface to a flowing stream is of interest specifically in the unit operation process drying, drying of inorganic and biological materials, that is, even in evaporation of solvents from paints or for plates in wind tunnels and in flow channels in chemical process equipments. Now, when the fluid flows past a plate in a free stream in an open space, the boundary layer is not fully developed. So, for gases or evaporation of liquids in the gas phase, and for the laminal region, which is defined by the equation length times the velocity times the density divided by the viscosity, which is less than 15,000, that is Reynolds number less than 15,000. The data can be represented within plus minus 25%. So by the particular equation, using the dimensionless factor J sub D, and it's equal to 0.664 times the Reynolds number raised to negative 0.5. Now, if you're going to express this particular dimensionless JD factor in terms of Sherwood number, that's the N sub HS, then it could be K sub C prime times L divided by the molar diffusivity B in here, and it could also be equal to 0.664 times the Reynolds number, the square root of it, that is, times the cube root of the Smith number. Now, where L is the length of the plate in the direction of the flow. Now, also, the dimensionless factor J sub D and J sub H here is equal to F divided by 2. Now, for this geometry, and for gases in which the Reynolds number or the Reynolds number is on the range 15,000 to 300,000, the data are represented within plus minus 30% by the two dimensionless factors here, J sub D and J sub H. So J sub D here in this particular region or velocity profile, 15,000 to 300,000 for Reynolds number, the appropriate J sub D dimensionless factor to use is this, 0.036 times the Reynolds number raised to negative 0.2. Now, experimental data for liquids are correlated within about plus minus 40% for Reynolds number within the range of 600 to 50,000. And in that case, if the Reynolds number fall on this particular range of value, the dimensionless JD factor that you're going to use is this. Whereas this is for liquids, whereas if it's for gases within this Reynolds number range, this would be the corresponding expression you're going to use. And this one is for gases or evaporating liquids in the gas phase. So this will be the J sub D. So you have different J sub D expressions depending on the value of the Reynolds number. So you can see from here that even we're going to look into mass transfer in flow parallel to flat plates, there's a need for us to establish the flow regime or the velocity profile. And that is, we need to know the value of the Reynolds number. Now, so this is a sample problem that will illustrate the formulas that I have given you here. So we are to choose the appropriate J sub D expression for our problem depending on the Reynolds number that we have pre-calculated. So for sample problem number 5, and this is the third to the last in this particular set of slides, a large volume of pure water at 26.1 degrees Celsius is flowing parallel to a flat plate of solid benzoic acid, where the length is 0.244 meters in the direction of flow. Now the water velocity is 0.061 meters per second, and the solubility of benzoic acid is 0.02948 kilomole per cubic meter. Now the diffusivity of benzoic acid to water is 1.245 times 10 raised to negative 9 meters squared per second. And the problem requires you to calculate the mass transfer coefficient K sub L and the molar flux N sub A. And that's the rate of diffusion of benzoic acid to the flowing water that is flowing above its flat plate. So we're going to answer this problem by starting off with an illustration, a clear illustration of the scenario that is stated in the problem. So let us go to our board for this. So this is our first problem on this particular set of slides. So we'll have this number 1. And for the given, let's try to draw a flat plate. So let's say this is our flat plate, and this flat plate is benzoic acid. Above this flat plate we have flowing water. So this water has the following information. So it's at 26.1 degrees Celsius, and its velocity is given as 0.61 meters per second. Now, so this benzoic acid here at the part wherein it's going to pass through, at the inlet part of the flat plate where it's going to pass through, we have the concentration here labeled as C sub O. Let's say that C sub O, and the part in here where it's going to leave this particular length of benzoic acid flat plate, will have it as C sub 1. Okay. Now there is this what we call interfacial concentration, or the interface concentration of benzoic acid right on the surface, and it's equal to, so I'd like to label that as C sub I, and it's equal to 0.02948 kilomole per cubic meter. So take note, this C sub I is on the interface, okay, for the concentration of benzoic acid. The flat plate of benzoic acid is of length 0.02, or rather it's only 0.244. So this is 0.244 meters. And the diffusivity of benzoic acid to water is given as 1.245 times 10 raised to negative 9 meters squared per second. Now A here being benzoic acid, and B is water. Okay. Now, what else is important here that we're going to write down is that here on the benzoic flat plate, we will label this as 0.1, and here on the bulk region where water is flowing above the benzoic acid flat plate, we will have this as region or 0.2. Later on, we're going to make use of this assignment of location in the formula that we're going to use. Now, for the problem, we need to determine the following. I light it here. The problem requires you to determine the K sub L and the molar flux N sub A. So as usual, we're going to start with the formula that would lead us to determining the unknown K sub L and our NA. We go to the next sheet and we'll start with our solution. Okay, now from table 7.2-1, which has the relationship between the different forms of the convective mass transfer coefficients, you can see that K sub C prime times C is equal to K sub L times X sub Bm times C. C referring to the constant concentration. Now, if the solution is dilute, in this case, we have a dilute solution because the concentration of our benzoic acid on the interface is just 0.02948, not even 1 kilomole per cubic meter, so it's dilute. So whenever you encounter such condition, your X sub Bm, this is the logarithmic mole fraction difference of our water from considering 0.2 and 0.1 location. So if it's dilute, if it's a solution that is dilute, this is automatically 1.0. If this is 1.0, so this is just like 1.0 and the C's are just the same, then we can say that our K sub C prime is equal to K sub L. So if we intend to find K sub L, we have to determine the K sub C prime. Now the question is, where will we get an expression for our K sub C prime? So there is this particular formula that I have shown to you a while ago, a formula which has the appearance of the K sub C. But before we can even use this particular formula, we need to establish the velocity profile, or we need to determine whether flow is laminar or turbulent, and specifically we need to know the range of the Reynolds number, or we need to know the Reynolds number so that we can check on what particular range does it fall. So in this case, we need to determine the Reynolds number. So our Reynolds number is given by the formula. Actually, the original formula for the Reynolds number is diameter times the V times the rho times the mu, velocity, density, and viscosity. Now, in our case, this particular diameter, since we're not on a pipe, we're not on a sphere, this will be the length of the flat plate. So this will be LV rho divided by mu. Now, we need to determine what particular rho and mu we will substitute in here. And again, since our solution is dilute, the rho and the density that you're going to use is that for liquid water. So for water, at the temperature which is given, which is 26.1 degrees Celsius, you need to determine the mu and the density. So we'll write down here the mu and the density. So your mu is 8.71 times 10 raised to negative 4 Pascal seconds, and your density will be 996 kilogram per cubic meter. Now, the next thing that we need to do is, of course, substitute here. So if you will substitute, the length of the flat plate is 0.244. This time, I will not anymore write the units. Then I have the velocity as 0.061, then the density, which is 996, and the viscosity, which is 8.71 times 10 raised to negative 4. This will give us a Reynolds number which is equal to 1.7 times 10 raised to 4. And this is Reynolds number which is 17,000. 1, 2, 3, 4. So 17,000 for the Reynolds number. So in that case, if it's a 17,000 for the Reynolds number, I'd like to go back to our slide and check where does this particular range or this particular value of Reynolds number fall into. So this one is for 15,000 to 300,000. And the formula that you have for this is for gases. Okay, this is for gases. So this is not a gas problem because what we have is benzoic acid. It's liquid, so we're not going to use that. So for liquids, here we are for liquids from 600 to 50,000 for Reynolds number. This would be the J sub D that we're going to use. Okay, you're not also going to use the one here on top because this one is for gases or evaporating liquids. We don't have the scenario of an evaporating liquid, nor do we have a gas. So the appropriate J sub D equation to use in this case is the last one. So I'd like to write it there on our board. So next would be the expression for the J sub D. So J sub D from the series of J sub D will be the appropriate J sub D will be 0.99 times the Reynolds number raised to negative 0.5. In this case, if we will substitute the Reynolds number that we got here, the 17,000, to this, your answer should be 0.00758. But nonetheless, this does not yet give us the K sub C prime which we're looking for. The K sub C prime, which is the K sub L that we have written here. So we need another J sub D expression to equate this with. That particular expression should have the presence of the K sub C. And what is that particular J sub D value or expression that will have the K sub C? This J sub D is K sub C prime times the Smith number raised to 0.67 divided by the velocity. Where am I taking this? This is for the J sub D equation when we were discussing the first part of this mass transfer coefficients in various geometries. So I'd like to go back to the slide to point this out to you. Where is this JD expression? So I'd like to go back for you to recall where that particular J sub D came from. So you get to see this. Okay? After we have discussed the four dimensionless numbers, Reynolds number, the Smith number, the Sherwood number, and the Stanton number, we have this dimensionless JD factor. This is where we get to see the K sub C prime. Now, in our case here, we cannot use the Stanton number because we're not even given this information here. Now, the Sherwood number is another number that we can use in here. This is an alternative that you can use. But in this case, I'd like to use this one because in the Sherwood number, we don't have the J sub D there. And what we have so far in our last part of the solution is a J sub D expression because when we look into the dimensionless number that we will use for a particular value of Reynolds number that we have predetermined, it's only the J sub D that we have as an equation to use. And of course, we will not use the other dimensionless numbers here in the start of the topic, but rather we will go back to the last part, which is the J sub D, because we will equate this to the J sub D that we have determined. So we'll go back to our We'll go back to our board, and we'll have this particular J sub D written. So this is the J sub D that we have written, and I will have that equated to 0.00758. Then I will have the K sub C prime. Then we'll have the Smith number here, which is 0.65, and I will have the velocity that is given, which is 0.061. I intentionally write it like this so you would know that for now you can't even solve the K sub C for now because you don't know the Smith number. So this becomes your first equation here. Let's check if this is the first equation that I have labeled. So this is our first equation. Now our goal is we will determine the dimensionless number, the Smith number. That way we can go back to this and determine the K sub C prime. So for our Smith number, the formula is mu divided by the density times the molar diffusivity. So we will now substitute values to our dimensionless number, which is the Smith number, and we're going to substitute the properties of water in this case at 26.1 degrees Celsius because we have a dilute solution. So for our mu, we have 8.71 times 10 raised to negative 4 Pascal seconds, and we have the density to be 996 kilogram per cubic meter, and we have the molar diffusivity of benzoic acid to water, which is 1.245 times 10 raised to negative 9 meters squared per second. This will give us a Smith number of 702. Now we have determined the dimensionless number, the Smith number, and we also have already determined our Reynolds number here, which is 7,000. Then we can now use this particular formula that will have the appearance of the Smith number, and that particular formula is this. So you have J sub D being equal to 0.99. By the way, this is the J sub D that I have written already here. So I will have to use a J sub D that will point us to the K sub C. And that J sub D is given by this particular formula. Now I will point out to you where this particular formula came from. So J sub D is equal to K sub C, K sub C prime, the Smith number, which is raised to 0.67, and all of this divided by the V. Now, where did this particular J sub D came from? So if you recall our initial discussion on mass transfer in various geometries or mass transfer coefficients in various geometries, we have started with the dimensionless numbers that were used to correlate data. So I'd like to go back to that part in our slide, the part which talks about the dimensionless numbers. And that part is this one. Now we have started with Reynolds number, then we have the Smith number, then we have the Sherwood number and the Stanton number. Aside from these four dimensionless numbers, we ended in this part with the JD factor, another dimensionless number, which is the JD factor. And this is where the appearance of the K sub C prime is seen. So we will have this particular expression used now and equate it to the J sub D value that we have predetermined, which this time under this particular topic is based on the value of the Reynolds number that we have predetermined. So if you recall, for this topic on flow outside solid surfaces, you have 3 J sub D to choose from depending on the phases, whether it's gases or liquids, and depending on the range of value in which your pre-computed or predetermined Reynolds number fall into. In our case, we use this one. So again, I'll go back to that part where we have another expression of the J sub D which is the starting part of this topic, the correlation of the different dimensionless numbers. So knowing that this is the J sub D now, that we will equate to our J sub D based on the geometry of the flat surfaces, we can equate the two values. So now the J sub D that we have here, this one, the 0.0078, will be equated to this particular J sub D here, which is actually I have written already in here. Just so happen that we still need to determine the Smith number. So from 1, so I'd like to say from 1 here, you'll have now 0.00758 being equal to, so we still have the K sub C prime and the Smith number, which is 702, which we will raise to 0.67. Now these two terms, the product of these two terms will be divided by the velocity. In this case, our velocity is 0.061. So this is 0.061. Now this will give us the K sub C prime, which is equal to, in this case also, which is equal to the K sub L, one of the required information in the problem. So K sub C prime, which is equal to our K sub L, is equal to 5.85 times 10 raised to negative 6 meters per second. So this is one information. Actually, the molar flux will just be a substitution if we know already the convective mass transfer coefficient to use. Now, as to our molar flux, the NA, that is, the formula that we will use is Kc prime. It's a generic formula actually, Ca1 minus Ca2 divided by the log mean mole fraction difference of B. Okay, this consider the mole fraction, the log mean mole fraction difference of point of B at point 1 and 2. And we have established already that this one's solution is dilute is equal to 1. So this is just a case of K sub C times Ca1 minus Ca2. Now, our K sub C, which is our K sub L, is 5.85 times 10 raised to negative 6 meters per second. And we have to multiply this with the Ca1, the concentration at the point 1. So in our illustration, our point 1, the starting point of the diffusion is from the benzoic acid flat plate, and our point 2 is on the bulk phase where water is flowing on top of this particular flat plate. So our concentration there of benzoic acid is given based on the statement that its solubility, so the term that was used in the problem is the solubility of benzoic acid is 0.02948. This is also the concentration at the interface. We view that as the concentration in the interface. So we will substitute that in here. 0.02948. The concentration of A, of course, in the bulk phase of water is not, of course, 0, but in this case it's very dilute and we have a large volume of water flowing on top of the plate, so we will view this value, since this is very small, to 0. But it's not actually that, it's not actually 0. There's a certain amount of benzoic acid because it has already diffused to our flowing water above the flat plate, but nonetheless its value will be very, very small to consider. So your molar flux in this case will be 1.726 times 10 raised to negative 7. Now this would be kilomole of A, which is our benzoic acid, meter squared per second. Okay, so this is the answer to the second requirement in the problem regarding the flux of A.